have slides for this first part, but I'm going to do more just the hands-on like we always do for that. So let me really quickly get to the place where I'm going to just start breaking into that. So, well, we'll do a quiz. All right, so Shane, what is that? What size? Obviously, it's a flow grid.
Yeah.
So what size would you say it is?
Maybe 2x1 or a 2-inch.
Okay. Which one? 2-inch. It's going to be a 2-inch. The 2-inch out in our system, there's a lot of standard ports and large ports. Okay. Which one is that?
That's a standard port. Or no? That's a large. Yeah, it's a large port.
It's a large port. How do you know?
The body.
The body. Because on an old standard port that hasn't been converted yet, it has the body, it has a spacer plate, a throttle plate, and a spring case. You've got 3 layers on the cake. When you transition it over to large port, the throttle plate's rounded and the spacer plate envelops it. So you know right from the road whether they've converted it over. Okay? What else do you know about it?
Mounting is top mount, not side mount.
Okay, so that'd be mounting position A if it was being purchased, yes?
Okay.
Do we stock like that or do we build them like that? The customer asks for it, yes.
Yeah, but it's
Right.
typically a side mount, right?
Typically a side mount. Why is that our standard?
Because it's easier to work on a Mooney regulator in the event that there's
Basic maintenance, because to do work in the body, just to inspect the diaphragm, put a rebuild kit in, I have to disconnect what is my outlet line, I have to disconnect my inlet line, and I have to disconnect my sense line, and the pilot comes off with the spring case. If I do it side mounted like that, I've got one thing to disconnect, and that is simply my loading line on top. And then I'm into the body. So that can be a benefit, not so much the way it's shown here. If they have space restrictions and they need to kind of like get things on top instead of on the side, especially if they're using a Welker filter or something, which is Pullman, they're tubing over, you can pretty much get real tight to that valve if you don't have that stuff mounted on the front. Okay. Anything else you notice about it?
Raised face flange.
Okay, raised face, what ANSI class? It's a 2-inch.
600.
300.
Probably 300. You only can tell by the thickness from this picture, really. Okay, but both of them have the 8 bolts. Here's its brother in the 150 class flange. Okay, so we know it's going to be 3 or 6. Looks to me like 3.
It's got the wrong filter on it.
Not stainless.
Okay. Should have a wall
It has an aluminum pilot filter with no drain. Okay, and it has a steel restrictor, not stainless. So from this, except for the fact that we can't tell without looking further what soft goods, what flexible element was put into the body, and what size throttle plate, which would be on a tag, should be on a tag here underneath one of these cap screws to tell us the capacity. We could completely configure that as far as the model. Well, that and the fact we don't know what the spring is in the pilot. We'd have to look at the spring sticker, but other than that. So this is what we end up doing a lot, where a customer says, I need a Mooney regulator. And sometimes the description is about that detailed, and they don't know anything. And so we ask them to take pictures, and we start giving them the replacement based on pictures around it. That gives us everything we need. Okay? A lot of times the serial number is what I go to for the rest, because I've got to figure out what throttle plate went in there originally or what diaphragm went in there originally, especially if the tag is all goobered up, and all I can get is certain information. The serial number is also stamped into the side component, so if I can't get it off the tag, I can get it there. Okay. All right. So some of the basic things about a flow grid, why it's so popular. It's ingenious in its simplicity. There's less than a dozen parts to the body. Comes apart extremely easy for technicians to work on it. It is vast in its flexibility. It has a tremendous turn down. It can have up to 300 to 1 turn down. I'll stop for a moment. Who doesn't know what I mean when I say turn down? It's okay, don't be shy.
Go ahead and explain it, Jeff.
Okay, so what I'm talking about is, and this is important with regulators, what you're talking about is its range of control from its maximum capacity all the way down to where it starts to lose control and start to cycle, on and off or open and close, because it can't find the place where it's supposed to be at such low flow that it just sits there and tries to open and close against, the input it's getting. Because when it opens, it seems like there's too much and the pressure immediately goes to set point, and so it closes again. You see a lot of valves that it's hitting that place where it's not able to control at the low point, and it's because it doesn't have enough turn down, doesn't have enough rangeability. So this has rangeability that can beat anything on the market, anything, okay, with the step drill hole throttle plate design, which we'll talk about, okay. It's a carbon steel body, all rated to 1,480 pounds. So the only thing that is going to determine which model we spec, as far as the body size and end connections, is what's going to fit best in their piping. So when we get to asking questions about application, we kind of want to know those things, so we spec the right connections, because the body doesn't care. It can handle the pressure. Okay. What's going to derate it is the connections. Yes, sir.
Jeff, I was just going to ask, and continue on the turn down, to determine the range, top and bottom, is that determined from the inlet pressure? Excellent.
Thank you. Okay, so I appreciate these things where I may not describe it well enough and I need to go into greater detail, because it's a simple thing to think about. Find the maximum pressure. When you understand what the turn down is based on the throttle plate you've put in, you just divide by that number. So if I say that turn down is 300 to 1 and the maximum capacity at a certain inlet pressure was 300,000, then at about 1,000 cubic feet an hour, that regulator is kind of start lowering its ability to be fine control over the gas. So it can go from 300,000 to 1,000. Okay. All right. So it's basically for gases, and there are, in the literature, situations where, they're saying it can be used for liquids, but we have better solutions oftentimes really for a liquid solution. So we're talking about gases and natural gases per se, specifically because of the soft goods. We're kind of in that realm because we have nitrile and various durometers and Viton to pick from in our soft goods. So if we get too exotic, this is not a good solution. Okay, we have to go to something that has a lot more exotic, flexible element choices, like a 900 TE. Okay, where we get EPDM and HMBR and blah blah blah. Okay, let's move on. Oh, and by the way, it's not good for low pressure cuts. Okay, so it does have its limitations. Among its many strengths, we don't want to use a flow grid when we're trying to cut 20 pounds of, have a 20-pound differential. So if I'm cutting, 40 to 35, I don't want to use this regulator. The reason is because we're talking about a valve that basically gets good shut off when it's got the ability to put enough pressure on top of the diaphragm onto the throttle plate to keep it shut off, even when there might be a little debris, even when there might be a little wear. So I want to make sure that that valve will shut off where it's supposed to. And the other thing is, you get these customers that want, like, I want, when I have only 200 pounds on my system, I want it to deliver 200 pounds downstream. Well, what they're asking for is a pipe at that point, not a regulator. The flow grid is not a good pipe, okay, because it's going to take a certain amount of differential pressure to get that flexible element to lift off the throttle plate and to allow that amount of flow that's required downstream to get to those loads. So there's always going to be a pressure drop in those situations where they're so close to where they really want to feed if the inlet pressure is already there. So Flowmax is way better at that, as an example. Okay, yes.
Can the Flow Grid handle liquids?
Yes, in some cases, thank you.
Jeff, competitive lines, you talked about the rangeability 300 to 1. What is a comparison to a competitor product?
Typically, you're seeing like with its competitors about 100 to 1. So that's pretty much where they'll reach. And you know, the Flowmax is kind of there when we put a low flow range extender in. So it's not, doesn't have nearly the turn down of a Flow Grid either. That's not one of its strengths. But that's about where our competitors are. So, I mean, you're so far ahead of that, it's not even funny. Speaking of that, we're also going to talk about the Flowmax, so I'm showing a cross-section of that. And this other product line we mentioned because of liquids and because of exotic gases and those kind of things, the 900TE. We tend not to stock that, but it does have situations where we spec it. We have engineer situations where they want to cut 1,400 pounds across a working monitor and they don't want to put an upstream regulator to try to share some of that pressure. Well, at least in this situation, we've got a body, it's real heavy carbon steel, real durable the way it's built. It can handle 1,200 pounds of differential pressure. The typical Flow Grid is going to be at 800 PSID under normal operations if it's 2-inch all the way up to its largest size, which is 12-inch. And in the smaller body, excuse me, sir, the smaller body size, 1-inch throttling areas, this 2x1, if it had 600 class flanges, it would be rated at 1,000 pounds single pressure cut. And those are under normal conditions. So if you had a non-standard situation where with a working monitor set, your normal shared cut was like 500 and 500, and one of those failed. This would see 1,000. Besides the icing, the block of ice that would be created if you didn't heat it, it could handle that. And if it was 1,200, under emergency conditions, it can handle a differential of 1,500 psi. So, you're still okay if it's not normal conditions. Okay.
Hey Jeff, on the 1,500 psi under emergency conditions, is that within a certain time frame? Like, does Mooney recommend it needs to be dropped within 30 minutes, an hour?
I haven't seen that like a time component listed with that, but I certainly think it shouldn't last. It should be as short a period of time as possible. Shouldn't. Well, okay, I lost my upstream regulator. I'll just go till next year and then I'll rebuild it. No, as soon as possible.
It's came up recently.
Did it?
Yeah.
That's something that Ken Graff, we can engage Ken Graff, and see what he gives us back. He's always a great resource. Okay, I mentioned we're also going to talk about the HP Flowmax. I do intend to do that. Really quickly, one of the obvious things you notice is how beefy this is compared to the standard Flowmax here, which we're going to break down. Okay, how much obviously has been built into this body so they can handle the pressure. You'll also notice how obviously the controls have changed. Okay, so when we spec this, strangely enough, you're speccing a restrictor, which we never do with a normal Flowmax because it has a restrictor pin which basically sets the proportional band that's basically going to balance between the bottom and the top. This is the restrictor right here on the downstream side or the back side of the pilot. It has a pre-pilot, and this all basically is blocked together, kind of like you get a controller box with a slam shut. So that all gets portioned. It's actually 2 parts to the order, and then of course what's not shown here is any kind of filtration. This is the way that the travel indicator looks like on that as well. So it's got a little different look than the pin that we're used to show the position of the valve being open or closed. It actually has like little graduations on it, so it's much more precise, much more exact. You have something to measure against, and there's a cap that goes over it.
Hey Jeff, did they keep the foam gasket that came around where you open it up still?
Well, it's completely changed the way you get into the valve.
Really?
So yes, so as an example, you have actually two choices, and you'll see this later. You can, if you want to just get into the body and inspect the area around the plug seal, the whole thing comes off and you have a real gasket there. And if you just want to look at what's going on with the diaphragm area itself, then you just take off another section. With the other one, it's a little more involved. Like if you're going to do a rebuild, you have to do the bottom part first and put it back in the body so the stem doesn't fall out through the bottom, and then you build you disassemble from the top down. Okay, so
That's awesome.
a little more modular here. Well, a lot more modular here. So I like the design.
Hey Jeff, would you just briefly mention kind of what drove them developing this product? 'Cause
Yeah,
it's been a process. for them.
absolutely. So yeah, like why do they think that they're going to be successful with this? Because the Flowmax has that ability to make very shallow pressure cuts. This is got the benefit of being very high capacity. Basically, a lot of times you can use a 2-inch Flowmax where you need to already have moved up to a 3-inch body flow grid. So very high capacity and the ability to control very shallow pressure cuts. So people have said, well, can we go above ANSI 150? Well, with that, the maximum inlet pressure is 250 pounds. So now we're talking about situations where people are saying, I want to have those features, the high capacity and the ability to have, low differential pressure in a higher ANSI class. And that's what this was answering the mail for.
Jeff, why do you think somebody would want to make a shallow cut like that with high inlet pressure?
Well, a lot of times they have such a big swing, if you will, in their conditions, or they're running so close to their MAOP, they don't have a lot of room. But they've got some very exacting requirements on the downstream demands that they want to make sure that they meet. So they want to make sure they're supposed to be exactly on the loads, but that doesn't require a lot of pressure cut on the upstream side, potentially.
To kind of add to why you could sell the other thing too, is the capacity itself is a lot higher than those flow grids in certain
Right.
situations. And so, like in Oklahoma, a lot of times, I'm usually in that ANSI 150 or below class. I can only sell like two 2-inch regulators and a worker monitor, and we'll put a Flowmax on the relief. 3-inch Flowmax, you want to do a 4-inch flow grid or something like
Right.
that. You can save money and get them the capacity they need.
Well, I think the first quote we did on that was a paper mill, I believe. And
Yes.
so it was high volumes coming into this facility that's using lots of gas, and but it had to be a very specific pressure
Yes.
coming into their equipment, and so in those high volumes.
Well, and you see in the distribution market too. So an example of my point that I was responding to with Tim, you might see swings on inlet pressure because of winter demands, that February at 7 in the morning, where their inlet pressures go really low. And that's where they have these crisis, if you will, in their system, because if they don't have a regulator that can basically be full open when their inlet pressure has dropped so far, that's be a huge problem with getting gas to their customers, and their downstream system drops. So with a situation like this, if you have the ability to be full open at 3 pounds, even when that inlet pressure has declined so severely, you've got a winner. So
We've actually had to go change out flow grids and put Flowmaxes in because of that reason, because of the supply pressure drop in cold temperatures.
It was a big problem solver for Mexico gas on the eastern side
Yeah.
of Mexico.
We've had to swap them out before because of that reason.
And think about the world where you're talking about, and a lot of these places where we're speccing F70 PRs and low pressure and stuff, where they're trying to control at low pressure, and they're also trying to relieve at low pressure, and the flow grid's out of the game. You can't set a flow grid, as an example, as a relief if they want to set less than 20 pounds, because you don't have the differential pressure to make sure it'll stay locked up. Flowmax, you can basically set it at 3 and you'd have no problem. Also, if you wanted to get to that point where you're trying to control at 10 inches water column with your regulation and then protect it with a flow safe, and you were starting with 10 pounds or something like that, you could never do that with a flow grid, but you could do that great with a Flowmax. Okay?
Hey Jeff, what was Mooney's real reasoning behind coming out with the Flowmax HP? Really just to compete with?
Well, I mean, I don't know whether they're competing with more than control valves. I don't know that there's really anything in the Fisher line that I could say adequately compares to this. I'm not sure. I mean, I know that they've had requests for it, like Jeff mentioned, but as far as a specific market share that they're trying to grab, I think we're talking about working against inadequate solutions now, and it was like we need a regulator that will do this.
Well, and to your point, they quote it like a control valve. So, I think in their mind, that just kind of inadvertently tells you what they think about it. But whether that's the case or not, depends.
One of the beautiful things, talk about genius and its simplicity, one of the beautiful things about flow grids too is its Lego kind of, modular design. If I start out with a body, I can snap on a section that basically slams the valve shut and never lets gas get to the throttle plate. Little controller box. Better not put that there. Come over here and look at this a break. This is all just basically starting as an FG30 2-inch large port flow grid that has a slam shut level on before the throttle plate and the diaphragm go on top of that, and then has a spring case on top of that. So it could be built, it could be retrofitted to any flow grid to have a slam shut level. Same thing with this other thing in the picture here, the noise controller. It's just another level that allows you to have that honeycomb style noise controller that can cut the, that can cut the basically the perceived noise, 27 decibels. There's always, when you're talking about noise controllers that are going in the body of a regulator like that though, a consideration how that affects your capacity. You basically put a 50% throttle plate in place when you do that. So a lot of times if you're dealing with a noise problem, you're also probably going to have to size up the valve body size because you're going to need more capacity. Just an aside. Let's get into the body itself. All right, so here we have the typical 2-inch large port Mooney Flow Grid that is side mounted. So this is side position C. It has a stainless steel pilot filter on because we always want to filter in some fashion what's going into the brain of this thing. The small spaces that are the amplification chamber of this valve. The small changes taking place here very rapidly and accurately cause a massive amount of flow change here. 1/8 of movement of a plug and stem assembly in this pilot can cause a couple 100,000 cubic feet an hour of natural gas to flow or be shut off altogether and lock it up. So very important to have some filtration, the best filtration. We always recommend a line filter in front of all of this because even though this has got small spaces and is the brain can't shut off a body that's got trash in it. So it's always important to filter there as well. Okay. So it has a restrictor, as you know, and we'll talk about the reason for that. And then it has basically gas that passes through this pilot and loads on top of the valve. It is an unloading design. In other words, the pilot has to let the gas come off the top of the spring case or off the top of the diaphragm for the valve to be allowed to open. So the gas pushes up from the inlet side and works its way over. The valve itself is completely bidirectional. So I have these components because I have 2 ports in the body that allow me to put basically the components in the direction that I'm planning to mount this. but I can basically mount those so that the valve's facing the other direction. And this is nice because I can have left hand and right hand runs where all my controls are outboard, so the technicians can easily access them and make their adjustments. You notice on my valve too that I have a capacity tag that's underneath the cap screw, unlike their example picture, that I don't have to open up this valve to actually determine what the capacity is based on the throttle plate. Did everybody get one of those capacity sheets? Good time to take a look at that while I'm taking this apart. So you'll notice I mentioned that this is a 2-inch large port with 150 class flange connections on it. If I know the throttling area, throttling size, which is a 2-inch large port, and I know the end connections, I then can determine the model of this valve without looking at the tag. Okay? Huh? 150 class flange connections, raised face, and a 2-inch large port.
29.
FG29, okay? So, this is an FG29 valve. If it was still a standard port, like many of them out there are, it has the exact same body, and it has, obviously the standard port throttle plate and all that. So what model are we, if a customer asks us for a conversion kit, what model are we starting with? 2-inch standard port, 150 class flange. An FG3. So this is what you see with that, by the way, before I go any farther, is here's those spaces or the layers I was talking about. It has a throttle plate, which is full face. It has a spacer plate that gives me the ability to let the diaphragm sit down and lift up from. It has a smaller interior dimension diaphragm, flexible element. You can pass it around so you can see why Zia Gas had problems with their regulators locking up when they had large port Mooney regulators and put a standard port rebuild kit in. It's because there's space around the edges then, the gas could flow, and the valve, no matter how hard the pilot tried to put inlet pressure down on that, couldn't get it to lock up. Okay? A lot of times it's as simple as that. And it's the challenge we've faced for the last 5 or 6 years since they made the announcement in 2014 that they were going to eliminate the standard port line and they were going to stop supporting it in 2020. Of course, on other business decisions, they might, like stretch it out a little more because they're making money off of rebuild kits, right? Yes.
I was going to say, Tri-State in my area, they're telling people that they went away with that. They said they retracted that they're not going to get rid of it.
And I heard that earlier this last year, and I approached our sales manager and also my customer service rep in Houston, and they both flatly denied that. They said that there's been no announcement. They're simply not cutting off, if you will,
By the date
the date because they were making some money. But it wasn't like, oh, well, we're just going to forget that, right?
There is a transition point, we just don't know when that's going to.
That's right. We still don't know because I don't think, at least as far as passed down to the level of the sales managers within Baker Hughes, that they have something. They up until that point, they want us to continue to buy. And they want the customers to do it at the same time. They're kind of working against us in one respect, is that we have heralded their message. We sent out their product announcement and told everybody the deadline. So, and we did our job of stocking to be ready to support that. Got a lot of people that have done what they need to do, but a lot of people have just procrastinated for whatever their reasons. We'll continue as best we can to support both groups, the ones that procrastinated and the ones now that have really started to get on board and configure as quickly as possible.
So just a story going on with Jeff's example here. We were in Center Point in Houston, Texas, Mark and I, and Steve, and when we actually purchased this Pioneer measurement, he was doing exactly what we described with Tri-Pack, Tri-State. He wasn't telling Centerpoint they had to do this by a transition date, and I'm telling you, the measurement manager was PO'd because it's a huge project to plan all the change-outs with all the standard four product they have out there. So he wasn't mad at us, but he was mad because somebody hadn't told him so he could start planning his business. And I'm telling you, if you hear what Matthew described, make sure you're telling the story that Jeff just told you. You've got to get these guys going because they are the poorest planners. They're going to push this project out as long as they can. We need to help them. Again, we keep them out of trouble, right?
Yep.
Push them into these projects.
You know,
Tell them what the
and a
story
lot of
is.
We may have a reputation with these other, like, you know, people out there in these other areas that sell product, and they may tell a lie, an untruth. They may see us as overly aggressive, but one thing we never do is we don't lie to our customers.
Yeah.
We always give them the best possible answers, the best possible solutions, and I think that speaks for itself. That's why we're growing.
Well, and at some point, and we've talked about this before, there's going to be a run on this.
Yep.
And we've been able to sustain the runs that we've had by keeping product in stock, but at some point it's going to get hard to
Well,
go.
Eric, you got that order
Yeah.
from Questar, our Dominion, years ago, and like 2 different orders. The Tri-Pack was, oh, don't worry about it, don't worry about it. And we're doing just the opposite, man. They're going to get rid of this. You need to start, at some point we get rid of it. We don't know when, but you need to start doing
You know, the ones that listen to us save a lot of money too, because
Well, that's what I
what
was gonna
is
say. They've
what has
bumped the
Baker Hughes
price.
been doing every year? They've been jacking the price up on those because they know that it's going to get more painful, and when you finally get around to it, it's going to make them more money.
Well, we got guys out Panhandle that are older, getting ready to retire, and they still have.
So,
the-
y'all see that this is completely bidirectional. There's no directional arrow on the body whatsoever. So whatever is going to be the direction of control of the gas is going to be determined by what I put on top of this, okay? All right, where's my flexible elements back? Did it get around? If not, we'll make sure it does later. I just need the standard port one back real quick. So we're going to rebuild this like we're starting from a standard port. So the way it would have looked then is we would have had a throttle plate down on a body O-ring. The body O-ring's job is to make sure that the gas is required to go over that wall, over the bridge, and can escape and go other places that we don't want it to go. So it is good when I can rub my finger across it and it's catching my finger. It hasn't lost its shape or its flexibility. If it gets hard or it basically gets where it's not returning to its original shape, out it comes. So typically when I get in to do inspections, if this system has been down for a while, I'm going to replace these soft goods anyway, because just like a diver, the soft good components that have been under pressure for years, they're going to get decompression sickness from sitting idle and not basically being able to effectively get rid of the gas that's trying to escape the material. It finds little particles of gas, it gets bigger, it separates the bunin and nylon, basically works its way out just like a diver getting decompression sickness would, blocks basically the blood flow to your brain and you die. So the diaphragm's doing the same thing. If it just sits there after it's been under pressure for a long period of time, it will basically deteriorate in its ability to still be in this regulator. Much better to train the techs. If they're going to go in and do work, go ahead, isolate the system, blow it down, do your inspections, do your rebuilds, and then get it back under pressure. If it's already sat there for 2 weeks before you do this, just plan to put a rebuild kit in it. It's going to be needing it, And I can show you multiple examples in the bins out there of these puffy looking diaphragms that came out after they had just, sat there like that. Well, I mean, what's the other solution? What do you do if a diver is getting the bends because he came to the surface too fast? You put him in a recompression chamber at the hospital, and you slowly, over several hours or days, bring them up to atmosphere. So that those little pockets those big pockets of gas get crushed back down to small again, and then slowly try to get them out of the tissues without damaging them. So.
But anymore, and I know you've been a proponent of this, if the guys are gonna break open the rig, they might as well just, it's really inexpensive, and they're not gonna have to come back and redo it later.
The question comes up a lot, Casey mentioned the thing about, how long can you be at emergency pressure? These things will come up where they'll say, well, how long before I have to change out the soft goods? Like what's the recommendation? The manufacturer recommendation is you go and inspect your soft goods annually and replace them as required. Okay, so, because, think about it. Think of all the various systems out there. Some of them are making massive pressure cuts with a lot of velocity, and there's a lot of wear on the soft goods. And then you have other ones that are just sitting there making, relatively modest cut, not big, huge changes in volume. City Gate Station example. It might be able to just sit there and hum along for years and years and years before you'd have to do anything to them. So we leave that to the customers to decide, but they need to inspect them annually. Yes.
Yeah, me and Terry went out to Hobbs to do that trial. I think those regulars set for 8 years. Those 8-inch flow grids they had out there, and they had all sorts of deformations.
Well,
and
they
stuff
all separated
at
the
the time.
dissemination, so I brought them
Yeah.
back, and they all.
But
Yes.
it's crazy.
So really quickly then, the first step that I needed to do to put this in standard port mode was to put my full face throttle plate down. There's a pin to align where the throttle plate will go down. Obviously I want to keep the divider on the same plane as the wall so that it has a way for the gas line to come up and over it and through it. Then I put my spacer we described. It has a place to basically bite into the diaphragm on one side and a need for a spacer O-ring so these two layers are sealed together. On the old style, it was just a groove in the spacer plate. And sometimes if you get a set of soft goods, especially if it's sat in a hot truck or whatever, these O-rings might not want to help you and get into that groove. We found that you put them in the freezer for 15 minutes, it helps to get these where they'll just fall in easier. So there is a certain degree of stretching or shrinking based on temperature. So then I can set that down and fill out and then get it go right back in. Okay, so there's my spacer. Then my standard port diaphragm. And by the way, when I pass this around again, notice that it'll say 60N on it here, and it says 14 in G. What this information is telling us is this is a 60 durometer nitrile diaphragm, which is very soft and flexible, good for low differential. When I say that for a flow grid, we're talking about under 60 pounds of pressure cut down to that 20 where I said we're not speccing it. That's the world that the 60 Duro would live in. And 14 is the year it was made. 2014 was the year that it was manufactured. The G stamp basically is talking about a process that they went to give these more resistant to that kind of decompression breakdown that I described. So if the G stamp is there, it's simply saying that it had a new annealing process to kind of try to keep this together during that process where gas was escaping through the material and try to keep it from separating. So that's good information. If you went to a set and you were working on it, or you saw them working on it, and they pulled one out that said 98 on it, literally that was the date it was made. And if that's the one they used, you know how long pretty much it's been in there without being replaced. Might have been inspected annually like they're supposed to, but without being replaced. And I'm not saying you'll see 98s, but I guarantee you'll see some that'll say 10 and 11 and stuff like that. That, they've been in there for several years because the process and conditions supported it is not going to get a lot of wear. So
I don't know how many times in the field I've seen them where they just turn it around a little bit and just keep on moving it until it gets to the point where it just completely breaks.
So what he's describing is, on a throttle plate, so I told you that the gas comes up through here and then basically goes to the other side to pass through. And it's our control over how much gas we're allowing to cross to the downstream side that is involved in that regulator's ability to, have that rangeability, to, throttle the gas and to shut off what it's supposed to shut off. So what it ends up happening is, since the control point is the downstream edge of this throttle plate, that's where it's crossing. That's where the wear occurs. So when you look at a diaphragm, you can tell which was the downstream side when it's pulled out, because that's where you'll see the heavy marks, the wear. And oftentimes, if they have no other, solution on hand, but they need to get this thing back operating, they'll look at it and say, okay, well, that's a lot of wear. I'll flip it over 180, and I'll make now where it was the upstream side, the downstream side, and give it a new wear point. And it works great. Okay, so obviously it's a thing that they should know in a pinch. We recommend if they have rebuild kits, put them in, because then you're not like, well, how long can it operate like that now before I have to do something with it? It'll be good for them. Okay, so I put my standard port diaphragm down. Then I have the typical mainspring that they're the same. So the new parts so far have been a throttle plate, a spacer plate, a standard port diaphragm, and then I can use that same old mainspring, and then a standard port, STD port spring case. Because the large port has to support the bigger pocket to give you that capacity, the standard port, this area here for where around the spring, the diaphragm is going to be able to lift is smaller. So when I put that down, that is an FG3. So what we're asking the customers to do is to plan for changing this to the large port so you can continue to get the soft goods and keep the regulator functioning, in perfect health by doing that. What's one consideration that the customers also have to decide? If you look at the FG3 and you look at the FG29 on those charts, and you look at, let's say they both had 100% throttle plates. The conversion kit we give them to large port has 100% plate because the original regulator had 100% plate. What happens to the CG? First of all, let me describe what the CG is. Who has a question? Okay. CG is a gas sizing coefficient. It gives us an ability to compare two valves and their capacity at basically the same pressure conditions. Okay, so if I have a higher CG, that means the valve's going to have more capacity. In this case, if I just put in a large port conversion kit, I've increased the capacity like 20-25%, depending on the throttle plate. What if this is one of those situations we were talking about, we want to make sure everybody's doing, and that is protect your regulators with a relief. I've just increased the capacity by converting this now. Can the relief cover that new capacity? We've got to talk to the customers every time we're doing this about, again, application. What's your system look like, right? So we can help them with that. What would be the obvious solution if they say, yeah, I have a relief and I don't want to increase capacity here? What can I do? Reduce the throttle plate size and the conversion one size. Okay, so if I was at 100 with an FG3 and I give them a conversion kit that has a 75% plate, what's the new CG? Exactly the same. It's not, so they're both 1130. It's not exactly the same in every step down, but it's really close. Well, what do we do with a customer that has a 35% standard port plate to begin with? And they tell us this. What are we going to do?
25.
There's a solution. It is this in here, okay? They have designed a 25% step drill hole plate that has a CG of 379, not on your chart, so you might want to make a note on the bottom or whatever. What was the standard port with a 35% plate? What was its CG?
380.
380. So now we changed to CG1. We gave them a solution that was pretty close to exactly matching. So that's what we would give them in those situations.
And it really hasn't been advertised either that they have.
No, and you know what? One Gas in Oklahoma, and a lot of thanks to Jeff, has been all over this. And we've made it really easy for them. And we could do this for anyone. They don't oftentimes know, because they might stock these so that they're ready to do these conversions when the technicians are going out to a site. They might not always know exactly what throttle plate they want in a conversion kit. We've always been in a situation where, hey, if you have bought a conversion kit from us and you need another throttle plate, we will swap you. We don't care. We'll get you what you need. You've already paid for it. Let's make sure that in the end your system works. So
I mean, they don't advertise they really didn't advertise the 25% plate.
yeah, they didn't advertise it at all. In fact, we pushed for them and said, we need this. And they go, oh yeah, we got something. And so then it became part of the price list. It wasn't part of the price list until KGM told them, we have to have this and we need a price for it. So the next year was in the price book.
Other advantages of the step drill hole plate versus a standard plate.
Okay, excellent. Okay, so we talked about this turn down issue. Okay, you can see this live and in color. All right, so typically if you're going to reduce capacity, and this one is a 75% slotted plate. I'm going to reduce the capacity by 25%. The way it happens with a slotted plate is they start with a 100% plate and they weld in restrictions at certain specific points. Okay, so the downstream side still has, when that diaphragm peels away, some places where it's blocked, but most of it, as soon as that peels away to that point, it's pretty open about as far down as the gas can reach. So when I do that, I double the turn down, but I don't do as well as 300 yet, because a standard 100% slotted plate's about 50 to 1. Okay? By putting in those restrictions, I've also increased my turn down, but not like this plate. Let me get the 75 and we'll pass them around together. Here's a 75% step drill hole plate. Now, I want you to look at the area closest to this bridge where this can go on, because it's reversible in this size. So it doesn't matter which one I pick as inlet or outlet, they're both basically shaped the same. But the ones on the innermost area closest to the wall are nozzle. Okay, so it basically has a shape where it gets smaller as the gas goes in. What this does is two things. First of all, when the diaphragm peels away, now it's only exposing one row of the downstream side, not whatever else is exposed from the slot, okay, and not restricted by the weld. So I have a tremendous amount of control over the low flow. Also, it moves the area of high velocity of the gas as it's flowing through across the plate down into the nozzles. So now my area of highest friction between the soft goods and that stainless steel plate is not right at the surface of the plate. It's down in the nozzle, so I get less wear on my soft goods. So it gives you benefit of both. So it's a great investment. They do cost more, but so does a slotted reduced capacity plate, because all of that welding in the restrictions you pay for. I'm talking about the customer pays for. So it's an increased price. Yes.
Does it give us the full 300 to 1?
Yes. So any of the step drill hole plates, that's where the 300 to 1 turn down is coming. And in my discussions with Ken Graff, he said that is their published turn down, but he would be okay with saying something much higher. So everything's a double-edged sword. We don't want to go with anything more than published. But here's you just don't want to put a step drill hole plate in everything because of that turn down. If you don't need it, don't put it in. If it's a shallow pressure cut you're making, and you have something that will flow a little bit of gas when there's just the smallest amount of differential pressure, then you're going to at some point experience lockup. I mean, if you had infinite turn down, you'd have no lockup. So you've got to understand and do the right thing for the process conditions. Okay? So again, you know, if we stay with our message to the customers, don't use flow grids when you're, you know, not making at least a 20-pound cut. That's adequate for a step drill hole or a slotted design. We really want, if we be quite frank, not to use them if there's not 30 pounds. You know, that's really what we would probably say is the normal minimum is 30 pounds. But if there's going to be 20, then we make modifications to what we're doing. So, well, you know, the specification sheets may say, okay, well, you're going to get, depending on the body size, full lift of the diaphragm at 8 or 12 pounds. But we know that there's other drawbacks that come with that, living in that realm, you know, as far as making sure it's not a perfect diaphragm, perfect throttle plate, no debris. So, you know, the laboratory conditions are not what we're spec'ing for. We want 20 or more pounds to give that added, you know.
You always said about 80% of what it's supposed to do.
Okay, so let's go into that CG number really fast, and we're going to do some sizing here in a minute. So what exactly does that give me? Okay, you have it in a general sense that it's kind of identifying capacity, but there's a simplified gas sizing equation, and it's in the Flow Grid brochure that's part of the stuff that I gave everybody. Okay, the simplified gas sizing equation basically says that if you want to solve for the CG, you just take the maximum flow rate, Qmax, which is in 1,000 cubic feet per hour. So you need to go to MCFH, you know, convert it over if they're giving you something else, you know, MCFD, standard cubic feet per minute, whatever they give it to you, you need to convert it to MCFH, and then divide that by the inlet pressure, P1, okay? And we're just going for basically a broad look, a thumb rule check at what the CG would be required for those applications. Because if I'm making a deeper pressure cut, I'm going to get the benefit of sonic velocity. I'm going to reach a point basically where I have critical flow, where I get a boost in capacity through the regulator. And I'll tell you basically where to look for that. If your inlet pressure is greater than 3 times your set point, you're going to be at a point where there's critical flow. Like if there's 100 pounds on the inlet and I'm cutting to 30, you're going to get about an extra 29% of the capacity into those conditions. If you set a higher set point with that 100 pounds, like at 50, you'll see a drop in capacity, even though the inlet pressure is the same. Okay, so again, just a thumb rule, if you have greater than 3 times the inlet pressure compared to your set point, you're going to see that boost in capacity, that critical flow, that sonic velocity. And we'll do valve spec and I'll prove it to you. Okay?
So that you can use this formula.
Absolutely.
Because of the critical
Yes.
flow.
And you have to kind of know, like you have to use this chart. If you go into valve spec, it's a catch-22. We're going to soon find here in a minute. Because you're going to want to size for the conditions to find the valve, but you have to have a starting point. You have to plug in some valve to work against that'll either tell you, oh, well, that's too small, or, it has, this or that issue. So the way that you plug in a decent possible solution is use the simplified gas sizing equation first. Plug in those and then see what that gives you when you put the process conditions against it. All right, so since we're there,
Hey,
let's
Jeff,
just...
Before you move on, can you just give a quick explanation of why Mooney moved away from the standard port and went to the large port with
Well, I think more than anything, it was a business decision. I mean, they had a large number of offerings, and so when GE bought Mooney, they said, okay, well, we've got all these like 2-inch dual ports. We've got Flow Grid 250s, which were with cheaper components. It could only handle 250 pounds max pressure. We have standard ports. We have large ports, and I think they decided that it would simplify and reduce their overall, requirements of what they had to maintain by settling on certain things in the 2-inch realm. And they also had the 2-inch added capacity, which they brought in as a way to try to keep in a 2-inch body and not go to a 3-inch because it has a bigger throttling area, a 3-inch throttling area. So I think probably more than anything it was a business decision, and they opted for the large port because it was more competitive against other 2-inch products as far as capacity goes. Okay, so the 1130 wasn't as obviously attractive if you were looking at capacity against some of the, you know, like a Fisher valve or something that was 2-inch. Much more competitive if you have that added 20-25% capacity. Okay, so let's go. If you want to, you can get valve spec up too. Let me get there. How am I doing on time, Jeff?
It is 11:20.
What time did I start?
About 10. About 10.
Okay, man, I gotta cooking, don't I? Okay, this is a picture of what I was describing on the step drill hole design. Okay, so the standard walls, if you will, of the throttle plate holes. This is basically describing in I guess where the high velocity is, the red green transition there was right up there on the surface. And what this is describing is basically how that area then moves down away from the surface of the diaphragm down into that nozzle. Okay, this is just showing you those marks on the diaphragms. In fact, we'll pass this around while I'm getting valve spec up. So these are the offerings of the diaphragms. You have an option for, this one is 75N, so it's nitrile 75 durometer. Good for from 60-pound cut, where we said the 60 duros live, you know, under that, up to maximum differential, which in a 2-inch body or larger was 800 pounds under normal conditions, okay? 1,200 under non-standard conditions. There's also a Viton option in 75 Duro. Viton is good for hot, gas conditions, and also sour, H2S type problems. So if I had H2S issues, I'd probably switch over to the Viton soft goods and the O-rings. I have another one here that's an 80L. The 80L is basically generally more durable, can handle higher pressure differential, like 400 pounds up, but it also is good in low temperatures. And then there's an 80H, which is the best option just for general wear resistance and for basically the higher pressures. So there's these, and there's one more floating around here already. Oh, here it is. Here is the 88. So you got a 60, a 75 nitrile, a 75 Viton, an 80L, and an 80H. Those are our options in flexible elements in a flow grid. Okay. I'm going to bust past some stuff on the pilot real quick. We can come back to it if we have time. Going straight for sizing. Okay, so this is what I was describing to you. Okay, the simplified gas sizing equation. Q, which is my maximum flow rate, Q max. If I was going to solve for, if I knew the CG of the valve, like I was going to use that one with 100% in the large port, so I would use 1420, okay, times my inlet pressure. And if I had sonic velocity present, which I described how we determined that, then I could also factor in that additional capacity, which is times 1.29. So that's how I could solve for what will this valve do for maximum capacity if I have an inlet pressure of 100 pounds and an outlet pressure of 20. Well, if I plug that into my sonic velocity present equation, the P1 minus P2 would be 80, divided by P1 is 100. The factor would be 0.8. That's greater than 0.64. So yeah, I have sonic velocity present. I can multiply in the 1.29. Most of the time, you're not going to have to mess with that because all you're going to do is going to try to figure out the general capacity so I can pick the right valve and then plug it into valve spec and let it work for me. Okay, but this works great if you're trying to help a technician and he's saying, I've got a situation over the years, you know, it seems like we've had trouble in certain like wintertime months with our regulators keeping up. Do we have the right ones? You get the process conditions or you give him this and talk them through it, and you can help them determine, do I need to increase the throttle plate? Is my capacity adequate under my current conditions, or has the system requirements grown beyond my current regulator's capabilities in those max flow conditions? So this is where that stuff can help them a lot. Okay, I can also, this is something we did for Black Hills, I can literally go into valve spec and build them the old traditional capacity charts. Okay, so all I do is in every term, using 100% capacity, I listed the old style dresser. I took the old style dresser, exact inlet and outlet pressures, and listed the capacities that valve spec gave me back. This is for the valve at 100% capacity, by the way. Jeff Good was mentioning something that I should bring up now. We never spec a valve and tell it to the customer based on it doing 100% of what they need at its maximum conditions. Why? Because we need a certain amount of safety margin for the things that we don't know. If someone tells you that, hey Cody, a regulator needs to be able to do 100,000 cubic feet an hour, okay? The hour part is the first problem there. If it does 100,000 cubic feet an hour at its max, does that mean that there are certain times when it's doing for a minute more than that rate? Sure, it's going to basically be possibly up and down. There's going to be within that hour times when the flow is, or the flow requirement is lower, and sometimes when it's higher. Okay, sometimes maybe when the pressure, inlet pressure might dip and the capacity might go up. So we always factor in 20% of what we're told is the maximum so that we can make sure the valve can cover it. And if we put two regulators working in series, working in consonance, a worker monitor, a working monitor, when they're set in series like that, because it's having to pass through one regulator and then on to the other, we always take off an additional portion. So we're actually going to use 30% as a safety margin, and that's what exactly what valve spec does, is it takes 30% away from their recommended solution, just to cover, if you will, what's going on both within that complement of the system and because of the safety margin we're applying because of those having the ability to flex. Okay, so this was done for Black Hills in 2-inch large ports, done for Black Hills in 3-inch, and apparently I've got lunch coming for it, but you guys should get orders from it. So they said that they needed these to do some sizing for Flow Grid. It sounded like a good trade.
So Jeff, did you send those out to everybody?
I sent this one out, so I guess what I'm telling you is this is just for what capacity. The 100%, I can give them to you for every throttle plate size, and I can give them to you for 2-inch. So I'll do that. So, yes.
As ultrasonics have been growing in our industry too, one thing with these regulators, I have similar customers who are changing out parts and regulators and start putting things in. Well, these vibrations in the lines start causing a lot of problems when they put these regulators in. They're undersized. You're talking about sizing, and they'll sit there and vibrate so much that the ultrasonics now is reading, saying, hey, there's a big problem in your line, something's going on. The acoustic signal that it's receiving is ridiculous. Something needs to be done in the line. Something's going on.
So it goes beyond just the regulators as far as the impact of that.
Yeah.
Remember what I was saying about sonic velocity? Look when I did the sizing and valve spec here. So let's just take the 100 psi inlet pressure. When the planned set point was 0.25, the solution was 511 MCFH capacity. It stayed that way, 511, 511, 511, as I increased the downstream set point, all the way to 20, still good to go. When I got to 30, it started dropping. Okay, so I'm right there at that point. This valve is starting to lose that critical flow, that sonic velocity. By the time I got really close, within 20 pounds, so I'm making a 20-pound cut from 100 to 80. Look, it's all the way down to 326 max capacity. So when we're doing our simplified gas sizing equation, we're not factoring for the outlet pressure yet. Okay, so that's why it's just a basic, like swag, you know, what do I plug into this formula? I need more information to give a more accurate idea of what its real capacity is. Up to the point where it reaches sonic velocity. Once it reaches sonic velocity, then it stays steady. So I can keep dropping the set point, and it doesn't matter. It's not going to get any more capacity than that. But once I get above that, like the downstream being a third of my upstream, I'm going to start seeing it shave off. Okay.
Yeah, that's linear, yeah.
Yes, it is.
You can see it on your
You can
chart.
see it, yes,
Okay.
exactly. All right, so let's actually do it in valve spec. Let me get that up. I showed you guys how to get CG and also where to get CG on the spec sheets. They're listed there on the spec sheets. That's what that other one is. Okay, so I'm going to actually escape out of this. I'm bringing up valve spec. Dun, 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 dun. So the first thing when you bring up the valve spec that I sent you guys, okay, is this screen. And it's going to look like something that's not for Mooney. So I want you to know exactly how to get into it. It says, when you bring this up for the first time, because it's also to support Mason, and it's to support Becker control valves, it's a tool for other applications as well. It's going to read flow control, water, liquid, CV calculation, blah, blah, blah. You're not going to size here. Okay, what you have to do, as soon as you open it the first time, is go up to item and pick new. Go down your laundry list so you see Mooney Regulator and click on it. Okay, once you've got that, now you've got sizing for a Mooney Regulator. And now we have to make new decisions. We have to give some input about the pipe size, the schedule. If you don't know the schedule, just put standard. Also, whether we're specing for a single regulator here, we're sizing for that. And also notice, it's already taken the 20% away we discussed. It's not going to give us, unless we tell it to and artificially do it, it's not going to size for the maximum capacity. Where we know that the maximum in every minute is at least that or less. So it's going to take that 20%. But I can go in here and do a reg and relief. I can do a regulator monitor. I can do a reg monitor and a relief. If I'm going to do a working monitor, okay, so just to be clear what a working monitor is, it's a two-stage cut with each one of these regulators able to, in addition to making a portion of the total cut, be able to make the full cut if the other one in the pair fails. So in order to do that, I put two pilots on this front regulator, with the second pilot, the monitor pilot, looking all the way downstream. So let's say in an example, I've got 1,000 pounds to 200 pounds to make as a total cut. And I have this first regulator go from 1,000 to, 700 or 600. And then I have this one go 600 to 200. But if, for whatever reason, this one failed wide open, this one has to go, to keep more than 200 from being downstream, this one has to be sized where when that pilot sees that flow go above 200, this regulator takes over and it goes 1,000 to 200 by itself. And the same thing, if this one has trash blow through it and it wipes it out and 1,000 pounds come through to the second regulator, this one has to be sized so that it sees at 1,000 pounds, it's still going to be able to control 200. Not standard conditions, but until the problem is dealt with, that's what this system is designed to do. And then of course, in addition, from all our training yesterday, how are we going to give secondary protection to this? A relief. Okay? So if the second one gets wiped out, you're still okay because it's going to pop off at, whatever, 210 or 220. So, okay. So let's just size an individual regulator. So I'm going to pick that. single regulator, 2-inch, inlet and outlet, schedule standard. Okay. I have to basically give it an idea of what I want to start with here on my flow conditions. Just name some flow conditions that the customer's given you. Give me some flow conditions you want to start with. How many MCFH?
150,000.
50,000?
150.
150, okay. 150, and I got to make sure I'm in the right unit of measure. MCFH, okay, for this. Okay. What inlet pressure? We're
400 down to 60.
400 to 60, and I want to do it in gauge pressure. If I don't do gauge pressure, what it's going to give me is basically an engineer's view. They don't know where this maybe is going to, the set or this regulator is going to actually go in their system. It may go in the mountains, it may go in the valley. So they're going to take the elevation and the gauge pressure out of the equation, and now we're going to have to factor that in later, you know. But so we're going to go from what our typical customer is going to say is, I need this pressure, and they're talking about their location, their problem, their solution they want from you. So we're going to go gauge. Okay, and give me those again, Nate. 400
to 60.
400 to 60.
to 60. Okay.
And could you
All right,
put this in
and
the form of a quote?
Normal default is 60 degrees Fahrenheit unless it's coming through some preheating or, you know, processing of the gas beforehand. Might heat it up to avoid Joule Thompson or what have you. And then I hit calculation, but if I don't put in an option here, it's not going to give me anything back. Let me show you. Okay, it gave me a recommendation. It said a 1-inch FG55. So if I don't put something in, it's going to pick something for me and then criticize it. So it's going to give me a solution that has enough room, but it's saying the outlet velocity is too high. Okay, so let's pick our own solution. It's saying that with this, the recommended CG is 350. Look at yours. Look at your capacity chart and tell me, in a 2-inch body, with what ANSI class would the connections have to be? 400 inlet.
300.
300. They may say 600 if the rest of the system is that, right? Because they don't want to deregulate it or degrade it. So yeah, it's probably going to be 300 class. Okay, if we're in a 2-inch body, what throttle plate in a 2-inch large port to give us a little extra room? So we want to make sure we have 20%.
35%.
Okay, which is a CG of
610.
610. Should be good. All right, so let's try that. We're going to select an FG30, and I can get there fast. I can say series, flow grid, size, 2-inch, rating class, 300, end connections, raise face, 35% capacity, apply filter. There's only one solution. It's an FG30 with a 35% plate. So I can get there that way, or I can pan down and then pick it. Once I say that and I say OK, it's going to put it in the solution right up here. And now I can recalculate. Oh, lo and behold, the dang velocity thing went away. We picked a better valve than the computer. So now I've got a recommended CG at 350, but I can I have an effective capacity of 610, so I'm okay there, and I'm only going to be at basically a little less than half open with a 100% plate. That if we don't have a minimum flow requirement, that would be a great solution. Noise isn't too terrible; it's below 90 decibels, so that's how you use this program. You want to see any other solutions with it?
Does it calculate pressure loss in like a working monitor or worker monitor? Actual pressure loss.
It accounts for it. It accounts for it. So you're not going to actually see, like, if you put this regulator here and then I try to put in another column, another one for the second stage. It's not going to degrade the second stage pressure because of the first one. Okay, if you're, under normal situations, if you're making a cut that's beyond the 20 pounds with these regulators, what you're losing in capacity is maybe a pound or two. You can see it obviously on a gauge, but, and this is why, good question actually, if I'm in a system where the pressure cuts I'm making are relatively shallow and I'm doing a worker monitor, let's say I only had 35 pounds of pressure cut to make, and I'm setting my, let's say my my worker's at 60, and I'm gonna make my worker inlet is at 60, or both the sets at 60. I'm gonna make my pressure cut to 25, but my monitor is at 30. So if I put my monitor up front, it sees full inlet pressure, and if it has to become the worker, it's going to be controlling at 30. So that's what I'm worried about. Is my critical point is what the monitor has to have. If it has to be the worker, so I probably put it up front in that situation, so it has full inlet pressure to work across that differential. If I put it downstream, because it's cutting, the worker up front would be 60 to 25. There might be a couple pounds lost that is in that, that differential through the body that now my monitor doesn't have to work with, and now I'm under the 30 I want from 58 to the 30-pound monitor. Could be much more critical if they're playing with this, like, well, they don't have 60 all the time. Sometimes it drops to 40. So now you're already talking about something that's really hurting to have flow grids there. And if you don't put the monitor up front, it's going to be worse. So that's like a lot of times what will happen is someone says, this is my condition, this is what I have. What do I do about it? How can I make it better? Well, a lot of times it'll be to do that. Do you have your monitor, up front in this situation? I definitely recommend it. We want whatever inlet pressure you have available to be available to that monitor that's set higher. So questions about valve spec? Okay. My time left?
It's 11:41. I don't know.
Okay. I think it's time to talk. Let me do this, because I haven't talked all about the pilot. You guys saw a little bit about that. Let me very quickly cover the pilot, and then I'm going to switch to the Flowmax, and then I'm going to switch to the HP Flowmax and wrap up. Okay. So obviously, you still have my undivided attention for the next 10 months and as a personal assistance anytime in my life. So it's not the last time you can have flow grid advice or training from me. But okay, so I'm using a brass Series 20 pilot for the conditions that we just talked about, where I might want to set what was it, downstream pressure in our little example. 60. So that's going to determine the spring range in here. So I'm going to pick a blue spring which has 25 to 90 psi range. So I want to try to pick one that has the right, obviously appropriate range. If I have two values, I don't want to be right at the edge of one spring. I'm going to use the one that gives me a little room to adjust. Also, if this is going to end up being a worker monitor situation, I want them to be able to switch between the worker and the monitor, give the worker a rest and let the monitor pick up and be the worker for a while. I want to make sure I pick a spring that both of them can be either. Okay, so anyway, some of the things that we saw yesterday with this is in how it's functioning. Say 200 pounds on the inlet, cutting to 40. Gas from the inlet side coming straight through this pilot, loading on top. It is basically keeping the diaphragm tight on the throttle plate, and not until the pilot unloads the gas on top by basically working against the spring tension that I put on this pilot to raise a little plug-in stem assembly up to let gas dump out the outlet. That means the gas on this side can escape and go out the outlet. That's what the restrictor is for, by the way, as well. These have to be together because this is like a little valve that lets less pressure through or less gas through than the pilot can dump out its outlet. It has to be there or the pilot can never get the gas off the top without this gas is constantly flowing through, loading back as quickly as it dumps. So This allows me proportional control of how big the hole is. If I make the hole bigger and put it on a bigger number, that means that the pilot has to work harder to get the gas off, so the valve's going to open slower. But when it needs to, like if it's close to MAOP and I want to make sure that I get this valve shut as quickly as possible, if I've got more gas constantly coming through to shut the valve, as soon as the pilot stops dumping gas, the thing's going to close very quickly. So the opposite, if I put it on a low number, I've got a very small hole in there, and so when the pilot says, I'm going to dump gas off, so because the downstream pressure is much lower than the spring tension that's keeping me, from being able to shut the valve. So when that happens, when the pilot is dumping gas off the top, this little bit of gas that's flowing through here and loading back is proportionally not going to be, much of a contest against what the pilot's doing. So the valve's going to open really fast. But the problem will be then, again, is the condition of how quickly it will close. So I've got to decide from a sensitivity or a stability perspective where I want this. Typically in startup, like the IOM manual will say put this on a larger number to keep it from cycling while there's gas just loading the downstream system. Most of the time you don't have to mess with this restrictor at all. Okay, but that's just a little trick if you look at the videos that they say. Let it sit at a higher number until basically it gets the line packed and then put back at 4. That's a standard middle of the road number. Questions about that? Okay. All right, so pilot. The pilot is very simple and ingenious in design. This thing is used all over the place, even on non-Moonies. People are constantly wanting to control their Fisher regulators, other brand regulators, with a Mooney pilot because it is so accurate, performs so well, and all it really needs is a place where the sense line is that's in relatively quiet gas. That's a critical thing for any pilot, but if I'm going to give this pilot the ability to control this valve in a really effective way, I want to make sure, now the manual will say, well, 8 to 10 pipe diameters downstream is the minimum placement for your sense line. The critical factor here is, where's the quiet gas? What I'm talking about is, I don't want to be near a change in direction of the piping. I don't want to be near another component the gas is passing through. A change in pipe size, like a step up or step down in pipe dimension. All of those things cause turbulence. And if I put my sense line in an area where the gas is turbulent and the pressure is fluctuating, the pilot has no chance to give you the tight control that is possible if you just put it in a place where there's a few inches or a couple feet of place where the gas can quiet down a little bit and become more bullet patterned and more laminar. Put your sense line there. The other thing too is, if I'm expecting this valve to respond to a really fast acting load, the asphalt plant kicks on, its furnaces or whatever, when they high fire, if this regulator is relatively close to that plant, it's going to pull that line down really quickly, and the regulator is going to have to catch up. So, real, high demand or fast run system, I want to place that sense line as close to the load as I can, not right up against its body, because that means it's going to detect that pull down before, and start opening and feeding that line before it's right up against its outlet. So that's a kind of a critical factor as well. Okay. All right. So pass these pilot parts around.
Jeff, do you think the flow safe pilot, like the P100, is equivalent to the Series 20 pilot?
The F100 shares some commonality with the Series 20 pilot. In my humble opinion, the Series 20 pilot design is superior, far superior. And if you ask me if a flow-safe F70PR or F7000 would work effectively with a Series 20 pilot as its control, I would say absolutely yes, and I think we should demonstrate it and prove it. Okay, so it all comes down to two things here.
I'm going to edit that out.
You saw this yesterday where it has 4 ports, right? The only difference with the F100 was it had 3 because the sense line was integral to the body, you know, it was up in there. So the one thing I want you to notice as passing around is the inlet and the loading ports are straight on the same level. The holes are on the same level. It says inlet and it says loading, but this pilot doesn't care. If you can't read, it's still going to work if you put the restrictor in the loading port and the inlet port is loading on top, because it's just a straight pass-through. That's how, by the way, when I make this for a left-hand run and my pilot's on this side, because I flipped the body around, and this became the place where I mounted the pilot, that's exactly what I'm going to do with the restrictors. I'm going to put it in a pilot that's sitting right here, and it's going to be into the loading port with the inlet loaded on top. So that's how I mirror image it, because it gives me the ability to do that. It doesn't care. All right. Notice then, if you look deeper in here, how the outlet is down, the hole for the outlet is down in that pocket. And what's happening there is, because this cartridge is up in that recess and it has holes on those levels separated by these O-rings to keep the levels separate. What I'm basically seeing here is these are the holes that are normally where the gas is flowing straight through, inlet pressure 200 loading on top of the valve, comes straight through those holes, and it's sealed by those O-rings. But when this comes off of its seat, which we're going to open this up in a second, it lets gas up through these higher holes, it dumps out the outlet. It dumps out this right here to the other side, creating a differential pressure. Now I have, because there's gas that's dumping basically out this way and out the valve, that can't be reloaded by the restrictor, I have less pressure holding the diaphragm down than is coming through here. So it's going to push its way through. Okay? And when my sense pressure is reached, that I set this spring in here to basically keep the valve open until there's enough gas to work against it. Once that happens, this little plug and stem assembly gets to pop back up, reseat the little valve in there, the little plug on an orifice, blocking that pathway out the outlet. And the only thing that's going to happen is that gas reloading is going to win and the valve shuts down, because I got 200 pounds back here. All right, so let me show you what that looks like real fast. New pilot, nice and tight. Okay. And there's a special tool that I need to get out the orifice. Paper clip. My kingdom for a paper clip.
Here you go, here's one.
I got one. Okay, because it has an O-ring that seals the orifice from falling out. That's a good thing. It's not letting gas around the orifice. I want to make sure it goes through the orifice. So I have to push it out to get it out. And there's the little O-ring, the little orifice O-ring has to come with it. And there's a little spacer to keep everything properly aligned. So I get this little, I call it an Oreo cookie sandwich, but it's really not the right colors or texture. But I have an O-ring and I have a spacer, and that's the place the gas is going to pass through to get to the outlet. Okay, when it's up in that little cartridge, when there's no spring tension on top, it's basically going to be able to seat just like that, and the gas is flowing under it, loading on top, just like that. But when I put that spring tension on, it's pushing this down like 1/8 of an inch. I'm going to exaggerate it just for purposes of demonstration. It's going to push it down, and there's all kinds of room around the stem for the gas to escape to the outlet, and the valve is open. It's literally moving that much to go from full open, hundreds of thousands of cubic feet an hour, to nothing, to zero. That's all it has to move. So just the smallest amount of the balance of forces between my downstream pressure and the spring tension moving this either on or off its seat is what's causing the muscle to control that much gas. Incredible, okay? One of those things that you have to talk to the technicians about then. My valve is not locking up. There's two things that possibly could most likely be wrong in a situation where they describe that. One is, this has been in there for a long time, it has wear on it or debris, it's got an H2S or some other particulate, they haven't done proper filtering, and they don't have a good seal here anymore, and there's gas leaking through to the outlet. Well, if it's leaking through, that means there's a slight differential pressure between what's on top of the valve and what's trying to get up from underneath, and the valve will leak. It'll pass through because of the pilot. The other problem could be that I don't have a good seal anymore because of wear on my diaphragm on the downstream side or whatever, and no matter how much 200 pounds the pilot puts here, it's doing a good job of putting that pressure there, it's physically got debris or some other thing that's not letting it seal off, and it's leaking through anyway, okay? One of the things that we teach when somebody calls us and is trying to do troubleshooting, and we're trying to teach them what to do about it, to determine, is it a body problem or is it a pilot problem in that instance? It's relatively easy. I need to isolate the two. So what we'll have them do is we'll have them basically disconnect this inlet tubing, spin the pilot off. It's really easy in A position, by the way. You don't have to do any of this. Spin the pilot off of this nipple, plug the body port here, plug the outlet port on the pilot, and then reassemble everything and retube everything. So the pilot's just sitting here, basically not connected to the outlet at all. There's no physical way then, if the plug and stem assembly is leaking, that it could be the cause of the valve failing to open, because it can't get gas off, off the top through this pathway, and it's the only pathway it has. So in that case, if it's still leaking, they got to look in the body. It's something to do with the throttle plate and the diaphragm or the seals. That's their problem. However, if that solved the problem, they can forget about this and get in there, change that plug and stem assembly, get into the cartridge and just make sure everything is assembled properly. The problem is in the pilot. It's that fast and easy. Take 5 minutes. And they can go through a lot of I changed this out and it didn't work, or I changed that out and it didn't work. Isolate the problem first, then go after it. So it's real easy. Okay, we can make this same pilot, by the way, high pressure, by just simply putting a spacer right where the normal diaphragm goes. Okay, so when I do that, when I put this back on the body you guys have, I've got a little physical room that I can see. The bolts are long enough where it'll still snap in. I get my 8 foot-pounds. Thank you. So it just fits down on there and I see a physical space. When I do that, now, when I put the black or the green springs in, which are used in the high pressure pilot, it doubles their range. So that's how I get to anything above 450. If a customer wants to set above 450 pounds as an outlet or a relief set point, that's how I get to it, is I will go to this high pressure pilot, and it's that easy to convert. It's just a little conversion kit. Obviously, if they buy the valve from us and we configure it, then we're going to give them a high pressure pilot. If they're doing something in the field and they need to configure it, we sell them a conversion kit, and it comes with these components. They just take the bolts off, reassemble that, and then put their black or the green spring in. It'll come with a new sticker that'll give them that higher double range. Okay. The one other thing that'll come with it too, and it isn't on this stem, but the adjusting screw stem on those real heavy springs has to have a way to make sure that I can't compress the stem and break the spring. If I didn't have this here and I ran it all the way down on the green spring, it's so stiff it might actually snap. So these are to prevent, they can still get the full value of the spring, but it'll prevent it from snapping. So this is basically something that they can install. You just push a little roll pin out, take the nut off, either put her on or off, depending on whether they need it. We've had situations where, as they use stuff in their system, they had a low pressure system with one of those on. So the contrary is true. If they had a red spring in there that was 3 to 12 pounds and they had that anti-crush, or anti-brake spring in there, call it a dwarven wedding band. If they had that on there, do you think they could get 10 to 12 pounds out of that pilot and set it? No way. The other thing, was Josh here? Remember that day we went out to that plant in Pryor and they had the Flowmaxes and they had red springs in and they couldn't figure out why they couldn't set the set point? And they had, what they've done is, I mean, it's like common sense that when you set the spring back in the spring case, that the follower goes nipple down so that this little adjusting screw kind of centers. They had this thing flipped over in there like that. I don't know how much we made on that call, but that's all we did and it worked. So it was awesome. Okay, so next, these lists of capacities, and then obviously there's a couple other plug retainers to consider, plug retainers to consider, but the CG values, the thing that makes this such a great tool is how much more capacity you get compared to a flow grid. We talked about the 2-inch large port being 1420, which was a boost from the old standard port, which was 1130. And we were saying, oh yeah, that's more capacity you got to consider. Well, I mean, you're going up another 40% with picking a Flowmax, which is fantastic. The other thing is, the Flowmax, whether it's this one or the HP model, they've stayed with the capability of 3 pounds, 3 PSID is full open. So when I get to the HP Flowmax, we get that same benefit. And also the HP Flowmax's by body size are about 5% more capacity than its little brother, than the 150 class. So it also shares that capacity benefit. Okay, so and I'll show you that here in a minute. So we talked about, like with the Pipes Act, how the target was concerned about, worker monitors that function in a common mode, and that trying to do something to protect because they could both possibly fail the same way. Using a Flowmax in complement to a flow grid would basically give you different modes of failure and different action of the valve. This actually will open based on the pilot lifting up the assembly where the stem is attached to. So it has to basically load to open, whereas a flow grid that we described has to unload to open. So they're not the same mode of function. In fact, the pilot that we're utilizing for this doesn't even use the loading port. So anytime you have a Series 20 pilot on a Flowmax, the loading port gets plugged. Don't need it. All we're concerned about the pilot doing is loading gas in to open the valve, and when the sense line, which would be run in this case from the top of the actuator downstream, when it senses that the set pressure has been reached, it relays that to the pilot and works against the spring and closes off this path that is letting gas lift, and the gas coming through the pin, the restrictor that's constantly trying to rebalance and close the valve, wins out and the valve closes. And it's basically pushing down a plug seal on an orifice seat, which we're going to look at in a minute. Okay, this does not have to be here for this to work. In fact, if it's the upstream valve, we recommend it come off, and we do it the traditional way. Traditional way being run the sense line downstream from this regulator just like you would from any other Mooney, run it from the pilot sense port, which means that instead of using this indirect path for the pilot to get what the actual downstream pressure is, we'll just give it to it directly, and we'll plug this port. We don't need it. The one thing that then has to occur differently is this gas that's up here has to still balance with what's downstream. Okay, so you need to run, if this is plugged, and we're running our sense line just like a traditional flow grid downstream from the pilot, then we run a return line between the two regulators that allows the gas that's up here to always be the same pressure as its outlet. Because one of the benefits of this is This chamber where the actual gas flow is occurring is isolated from what's happening under and above the diaphragm. So there's no way that what's happening up here with the pilot lifting the valve and the equalization to try to close can interact with or leak to what's happening below it unless the O-rings on the stem have failed. We had one situation, it was a 6-inch Flowmax we bought, and none of the assembly along the main stem was tight. And they took it out to be a relief somewhere, and it was leaking. So they brought it in here so we could solve the problem. I completely disassembled it and reassembled it, tightened everything down, worked like a charm. It was just a matter of, it couldn't do its job because all the places it was supposed to seal along that main stem that was supposed to be moving, it had play. So we were able to solve that problem without having to send it back to the factory and take months while I figured it out. So it was nice. Okay, so running the sense line from here under normal conditions, plugging this, and then just running a return line. That would be the upstream valve. Or if this is a relief, we will make the cartridge in back pressure mode, which we haven't discussed, so I'll show you how to do that. And we run the sense line upstream. So we're looking at that overpressure condition, and then the pilot is going to, when it sees that overpressure condition, lift the valve. And this simply then would be a return into the relief stack, because when the valve is open, there's gas coming through this pin, because that's what the restrictor is doing, is trying to rebalance. Which means if there's gas up here that's exhausting, we want whatever's coming, into this chamber to join that and leave with it. So you could put a bug screener here, something like that, but it'd be real hillbilly. Just run a line right here to the exhaust stack and handle it that way. Okay.
So Jeff, the customer's going to have to supply an addition when we plumb it that way. That dump, I guess, is what you could call it.
You need a weld-to-let
Weld-to-let right there, which is a little unusual. We'll need to tell them ahead of time.
Mm-hmm.
Okay.
And that's on the
Yeah.
exhaust stack, so it's
Yeah.
unnormal to what?
Right.
It's on either
Typically, there's a
regulator or relief. It needs a downstream
Yeah.
dump line.
Typically there's a conversation between us and the customer about if they're buying it for a worker monitor, what it is that needs to happen, and tell them how we're going to set it up for them. Tony Saletti at Kansas Gas Service, just a month or two ago, they bought 6-inch Flowmaxes, worker monitor. And we told him about this, and he had us identify in the crate which was the worker, which was the monitor, that we were setting it up this way. We'd plugged this already for him, that he'd have to run a return line. And so as the engineer, crafting the project, he was going to make sure that the guys put that in. So, I'm sure it's already done and running. So,
Jeff, can I ask you, just to clarify, if you're running the dump line downstream, it's the fourth, say that's
between the regulators.
Between the two regulators.
And in fact, this is why we're doing it, because if we do it by the Mooney IOM manual way, and it's hooked up just like I've described, right? This is the upstream regulator. The pilot is actually getting sense pressure through this upper chamber above the diaphragm. The sense line's being run downstream of the second regulator. And one of the possible failures that we've talked about with any pilot operated regulator is that this plug and stem assembly, or the spindle and nozzle, or whatever the assembly is, leaks. Okay, doesn't have a good O-ring, doesn't have a good plug on it where there's debris or there's notching or something. Gas leaks. Well, what happens when a gas leaks on a Flowmax? It comes into this chamber and lifts the valve. So it's not going to lock up. Well, where does this go if it's the upstream regulator and a worker monitor? It goes into this chamber, down the sense line, around the second valve, and keeps feeding the system with the leak, even though this one said, oh, I'm at my pressure and I need to shut. I need to lock up. So that had to be eliminated. We know that that's just a common, place that there's a possible failure. It's not likely, but we've got to take care of it. And it has caused problems.
Didn't we have that with Daryl Ritter?
I think so.
It was
Yeah.
Rick Ritter, because he had him in that setup and couldn't figure out why it wasn't working
Well,
right.
the pressure kept building downstream.
Right.
Other regulators.
And then he came in, you showed him the revised drawing that you had done versus the one in the IOM manual, and he goes, well, that makes sense. But it was just, they were going off the book, and the book was wrong.
The standard way that the valve would come in fully configured is okay for the downstream reg. That's fine. Personally, though, if they get into the habit of just running their sense line whenever they use a Flowmax from the pilot, like everything else, and just have this plugged and know they have to run a return line into the downstream piping, that would be better in my opinion.
Jeff's got a revised, you've probably seen it, but he's got a revised kind of drawing of that with the correct way to plumb that.
Okay.
So,
It's the one in the handout that I gave you guys. It's actually part of this presentation. I gave you the one where it has that exact piping configuration. Because one page is correct, the other page is not. But it's only not because they're trying to say, well, if the monitor is in this position in the set, you can do this, and if the worker is in that position, you can do that. It doesn't matter. Worker monitors, either one of them has to pick up for the other. That's the nature of it. So you should also be able to switch them. Okay, so what I'm going to do, one of the nice things about this is this looks like it's more involved than a flow grid, but the maintenance is actually, if anything, lower, except on a full rebuild, which because the soft goods in this don't experience anything but like static pressure. There's no like high velocity gas flowing across any of the seals or anything like that. So the balancing diaphragm in the top, the O-rings along the stem, all that stuff could go years without having anything that you need to do to them. And then once you actually go to rebuild it, it really is very, very step-by-step and fundamental. The hardest thing is you've got to end up detaching these bolts along the actuator, the diaphragm case, so that you can separate them. That's the most involved. But most of the time you have one thing to worry about, and it's a plug seal. It's a donut of nitrile that's actually your sealing surface. And when it has some wear or whatever, you can flip it over and use the other side. So you don't even, a lot of times, even have to do anything about putting a new one in. Do you mind holding right here? There's an O-ring seal that actually is the gas seal. There's also a cheesy gasket, which is really nothing more than a hindrance. When the customer first tries to take this apart, if it's like bound with paint, it'll probably tear. So we always have to cut it the first time. But it's basically a turn and twist up. This is the goofy water. It's basically like a weather seal, just to keep things from getting in there. But this is the real gas seal right here. So we could only, if anything was, like if that was left out, if anything was to be a problem, it couldn't get any farther than this ledge anyway. And on the 6-inch version, there isn't a gasket. Okay, so what we have here, very traditional orifice and an opportunity to have the capacity set instead of by throttle plates, by plug seals. So on the stem you can see that. This actually is where this is setting down. Okay, the knife edge of that orifice is what's sealing against that exposed nitrile there. That's when the valve is shut. When it opens and gas is the gas that the pilot's putting through lifts up, this pin actually gives a telltale. It shows you the valve is open. You see the pin? Can you see it? Okay, so that's similar to the HP model, except a little bit more exact on that one. But so if I'm going to change capacity where I want to improve turn down, because obviously this kind of a design is going to have low turn down, not very effective turn down. So if I had a low flow issue where I needed to control lower, I'm probably going to need to do something about this plug retainer, because when it comes off of the orifice, it's off. And you got a lot of flow through there. Okay, so if it's really, yes.
What is the turn down compared to the LFRS?
Okay, well the LFRX gives you 1% control, so 101.
Right. So what's
This is running probably somewhere in the vicinity of like 20 to 25.
Okay.
Okay, so you're gonna, if you put any of the other plug retainers in, it goes up, you know, like 33, 35, somewhere in that range. Okay, and it's as easy as this to change out the capacity, like we're gonna change throttle plates. You hold the stem, because you don't want the stem to rotate, because it's basically connected to all the assembly as it moves up. So I hold it in place. It's got a notch on the stem that allows me to do this. And then I just loosen this stem nut. And then sometimes if it's sticking to it, you know, you have to gently pry with a light screwdriver or something, but you just pull the plug retainer off. Usually you get it started, it'll come right off. And this right here is your sealing surface. This little donut is your diaphragm, okay, in essence. Okay, so it's what's sealing, and if you have anything where you look at it and say, oh, well, there's wear there, I think I'll just flip it over and use the other side and put it back on. Okay, so it's that easy. We stock these, you know, by the dozen. So if you have a Flowmax customer, this is something that they'll want to stock. They don't need to stock the whole rebuild kit with all the O-rings and all that stuff, except maybe one in case they have an issue and they need to go farther. But 95% of the time, this is the only maintenance required is take 2 bolts off, lift off the actuator, inspect and replace the plug seal, put it back together, and go. The only place the gas is flowing across is a flexible element. Okay? Questions on that? Low flow range extender, you hear a lot about it. Low flow range extender basically just mounts in place of the 100%. I put my nut back on that holds it there. And what I get is initially when I want control of low flow and I want the valve to be partially open and to manage that low flow better, this is what it looks like. Same situation, but instead of when it lifts up, it being wide open, like right there, I've got for the first like 1/4 inch, it's still inside the housing of the orifice, and the gas has to flow around the tight tolerances between the two. Not until it basically clears it all the way do I get full flow. So I lose about 15% of my top end. The CG is like 1970, still way more than a large port. And I gain back quite a bit of that low flow rangeability. So this is very popular with you know, trying to use these as regulators in systems where we have quite a variance in flow. If I need to worry about that relief with these and I need to trim down some of that high capacity because I don't need it all, this is a 25% capacity plug retainer. So when it goes down in the orifice, it never comes out all the way. I mean, the lift is really about a 1/2 inch, so it comes out about that far. Never leaves, okay? And whatever the 25% is flowing around it. 50%, a little bit more radical angle. 75%, more aggressive still. That gets me 75%. And then you saw the low flow range extender. So I have actually 5 options of plug retainer, from 100 to essentially 85 with high turn down, 75, 50, 25. In the larger sizes, I have 3, like a 6 inch, I get the 100, I get the low flow range extender, and I get a 50. Okay. What questions do you have about the Flowmax? Anyone? Still use them as, like I said, worker monitors very well. You work fantastic as reliefs. We can mount a Series 20L pilot instead of that pilot. and get those like 10-inch water column on up, set points. If it's a relief, really 3 PSI and up, we can use them as reliefs. That's going to get us our full open at 3. Yes.
So the lower portion of that Flowmax obviously takes a lot of the dirtier gases coming through, and there is some gas exposed in that top area of that diaphragm, where like the rebuild kit would be. How often have you really seen people have to go out there and put a full rebuild kit and clean that thing out because debris or something's caught in that top?
What he's talking about is this is hollow on a standard Flowmax. So while this thing is waiting to lift, it's also basically putting gas at inlet pressure up into this top chamber, so it sits on top of a piston. It's the exact same surface area as the orifice itself. So downward pressure with that gas, aided by a little spring, mainspring to give closing bias. So the question is, if I've got problems with dirty gas, do I have to worry about getting into this chamber and cleaning that out? I've never seen a situation where just a little bit of whatever rust or whatever above that piston and the seals has actually affected the seal itself. It has a skirt, so I don't think it's a problem, but when they go to rebuild it, they will or may find that there's a little, trash up there. If it was bad enough to actually block that chamber, though, that would be a problem. So that would cause the valve to not want to close fully, because that's your help to get it closed. So another reason to always use filtering with regulators, not let them be your strainers.
Can you flip those up as a working monitor?
Working monitor? Pretty rare, just because it's an ANSI 150 regulator. That would definitely be the case with the HPs. But because it's an ANSI 150 regulator, it's not very common to see that people want to make 2 cuts plus have each one back each other up. Usually that's happening when they're wanting to share a relatively large cut, maybe share also the temperature drop due to Joule-Thomson. But it's not something you couldn't do. Like if that's something that they want to do, like cut from 225 down to 5 and they wanted to share that between them, yes, you could set these up as a working monitor, just the same as you do with Flow Grid. And just basically the same process. So anytime you're doing a working monitor, so let's start with a Flow Grid. Well, I'll use this one. Okay. Whenever you're using a working monitor, let's say this is the upstream regulator, because it's going to be double piloted. Can everybody see this, or is it going to lift it up, or can you get to it? Under normal conditions, I have a restrictor on it. The outlet is for this pilot, the main pilot controlling, what's happening with this regulator. Its outlet is mounted into the body. When I double pilot this, I have to put this pilot with its inlet connected to the outlet of that pilot. I plug the loading port, which is here, okay? I plug that, okay? And I run the outlet of this valve into that outlet. So normally this stuff is turn 90 so that I can get these two together, outlet to inlet. That now the outlet that this valve is gonna use is the outlet on my monitor pilot, and this stays the same with the restrictor mounted in there. What I'm doing, just because it sounds complicated, is I'm putting this pilot as a path that this pilot has to go through to get the gas dumped off the top. And this pilot is not even worried about what's happening, downstream of it. So if this is making the first stage cut, and then there's another regulator, this pilot sense line is downstream of both of them, just like it is if it's a worker monitor. And its job is just to sit open with its, spring higher than the downstream pressure, so it's basically going to just be a straight through path. It's going to be out of the way, unless that regulator fails to make its cut and the pressure starts to rise. Then this pilot will sense it, and now it'll block the path for whatever this one is doing, and it will take over. It will only let gas dump off if it says it's at the right pressure, which is what it's looking for down there. So that's how you set up a working monitor, is that one intercedes between the two. All right, well this was, and this is on the wall out there, by the way, too. This a little bit deceptive because obviously this supply line is in the body, you know, and it's coming out of a pilot filter, but it passes through the pilot, goes basically straight into the area underneath that diaphragm plate and the underside and lifts the assembly. You can see basically the assembly with the various O-rings and that mainspring I was describing, and also the hollow shaft that's putting inlet pressure up there. Okay. You also see that the sense line, this is obviously indirect, back into that top chamber with that little restrictor pin constantly trying to balance what's on the inlet side to the outlet side, and then indirectly the pilot getting that sense pressure. So that's what that's trying to demonstrate. Obviously we're saying take it straight from the sense straight from the pilot, and don't do it that way. This was that diagram I was telling you about that we recommend our customers do when they're doing a worker or an operator monitor, where the front pilot is taking its sense straight from its own sense port downstream of the second regulator. That place where there was a connection is plugged and a return line between the two. And then the second regulator can just be set up like it normally is, with the sense line into the top of the actuator and then the sense line hooked downstream. Or you could do it just like this one, which is run that dang sense line from the pilot, get rid of that, and do your return line. Okay? Talk about those. Talked about the LFRX. I want to get to, and this is the back pressure mode. We did a drawing to show people how to do the pilot to the upstream side and still use the return line. So this is kind of done, even though it's not a very professional drawing. I just wanted you to have it. Okay, this is the way we do, like Casey was describing. We put everything together for them and describe it all. This was one that was set up as a relief, where we're basically giving them the fitting for the return line. All they have to do is do it. They've already got a swage lock connection to go upstream from their pilot directly, so it's hinting for them to do it. And the cartridge has already been changed to BPV, so all they got to do is just drop it in and tube it, tube up their sense line and the return line, and they're golden. Okay, now we're going to the HP. This is, I have a little bit of pictures of a takedown, a rebuild. Someday we'll get into that. HP Flowmax. Okay, so we talked about the fact that it's a fail-close design and that it basically gives you the same features as a standard Flowmax, but in 300 and 600 class, rated to 1480 PSI. Okay, still goes full open with as low as 3 PSID. Okay, it has heavy construction for handling that pressure. Some similar things, some things are different. You don't have that like orifice with a plug seal. You have a piston down here that's moving up and down with the shaft. And when it moves up high enough, the gas escapes through this port right here. Okay, the balancing is occurring not by gas going through the hollow shaft anymore. It's actually coming from the ports from the restrictor. Okay, back and forth. Okay, so here's what it looks like from a side view, and you can see what I'm describing. So there's those two ports on the upper and lower side of that diaphragm. You have a sense line that's run from the top of the actuator that's sensing that pressure, and it's being sensed all the way back down through the restrictor to this pre-pilot. So the pre-pilot is using what currently is the downstream pressure, and it's moderating with what the inlet pressure is, how much gas is going to this pilot. And then you have a little adjustment on the side of that restrictor, which this is the Type 27 restrictor. You have a little adjustment for proportional band like you do on the Type 24. So it's going to give you the ability to adjust responsiveness of opening and closing. But the pilot then delivers the gas underneath, just like on the other one, that assembly that lifts the piston and lets gas flow out that port. Still, you have very fixed separations that you can, when you do maintenance, is very easy. You can basically just do the top and get in and do maintenance on this. You can pull the whole top works off with these, and the stem comes out, and you can do maintenance on the piston or in the area of its seal. And I was telling you the CGs are slightly better. Remember, 2250 was a CG of a 2-inch standard Flowmax. It's higher here. That's higher, and that's higher by a little bit in each case. So we retain the high capacity, we retain the low differential or control at low differential pressure. So all those things are consistent with probably a little better design overall. This is how you spec it. So an ordering guide, this is for folks that are going to use that price book and you're trying to figure out how to spec it. Kind of like, this is real similar to the FlowSafe stuff. It tells you how to build your model number that you're going to order.
Hey Jeff, I'm sorry, real quick. I saw you had class 300, class 600.
Yes.
Okay, so is there a 300 or 600 or just one that's 600 that'll do both?
300 and 600.
Okay.
So in the 2-inch, the 300 class flange connection one is an FM14. Okay. Or an FM14T if you want that traveling.
We had that discussion. I think it was with the one guys here about. I think it was related to whatever that high pressure zinc that they were talking about at one point, and they were a little adamant about, well, we're not going to put it at 600 in a 300 set, and you know what I'm saying? Mm-hmm. Just anyway.
So they don't have to. They can have exactly what they need. And it's the same thing with every body size. So if it's a 300 class 3-inch, it's an FM15. If it's a 600 class 3-inch, it's an FM19. And this is what's coming in a couple of weeks that we're going to play with. It's an FM21, a 6-inch 600 class HP Flowmax. Ooh. And so then the other things that we have to identify. Do we want a travel indicator or not? We always do. Standard cage, that's what we're normally going to get. We're going to have to find out more about when we might want to use this double stage linear, single stage linear, blah, blah, blah. Don't know yet. Don't have enough information. Maybe what Casey sent with the IOM manual might shed some light on it. Then you pick your pilot, and this is your main pilot. The pre-pilot's always kind of a standard thing. And it tells you the spring ranges, which are, amazingly the exact same spring ranges that we're used to. But they just identified the models. And they're probably the same stainless steel pilots, they're just now in this manifold. Okay, and then a restrictor, which is unusual for us, but you'll have the restrictor, which is on the downstream side of that block of the pilot. And then the type of mounting, typically the side mount is pilot front of valve. And then what sense line option you want. The standard is A with a 1/2-inch NPT common sense. So if you want, you can get 1/4-inch NPT, but with the size of that valve and the amount it's going to flow, I think that's why their standard is 1/2-inch. Okay. And that's a picture of the top of top works, where you can get in with these bolts, basically pull that out and inspect around the diaphragm and the mainspring, that type of thing. This is the bottom part where you can see it still has that plug retainer, plug seal look, where it goes down inside the diaphragm to give you better rangeability right off the bat. But what's improved is this is all kind of in a piston style, and it has to lift to that point where the angle of that's exposed to that chamber. So you have a range there where it's not just full open right away. It's going to have that turn down. Okay, let's see if there's anything else. This is getting to what Will was asking about how easy and how modular it is compared. So if you just want to work on the bottom portion, you can take the whole assembly of the top portion off and get right to it. If you just want to get to the diaphragm and that kind of stuff, then you just take the first row of bolts off. So you don't have to go through this whole thing of you got to get to this, to get to that, to get to this. So that took him quite a while one day when he was rebuilding one.